Everything you see and touch might be built from tiny vibrating strings. That's the core of string theory, and it makes a shocking claim. For the math to work, for reality to hold together, our universe has to have hidden dimensions. Beyond the three of space and one of time we know, they're not far away. They're curled up into a microscopic realm, existing everywhere around us right now. These dimensions are a mandatory part of cosmic architecture. They could solve physics' greatest mysteries. We'll explore where they're hiding, what bizarre shapes they might take, whether we'll ever find proof they exist, and what it means for our basic understanding of reality. If we're truly surrounded by unseen worlds, physics was in a state of quiet panic. There were these two magnificent frameworks for the universe, but they spoke completely different languages. You had Einstein's general relativity, this beautiful, continuous picture where gravity is just the curvature of space and time by mass and energy. It explains planets, black holes, the expansion of the cosmos. And then you had quantum mechanics, this frantic, probabilistic world where particles can be in two places at once, popping in and out of existence. It describes the forces inside an atom. The problem was, these two theories are fundamentally incompatible. If you try to apply gravity's equations to the quantum scale, the math just breaks down. It gives you nonsense, infinities. It was like the universe had two rule books that contradicted each other. For decades, that was the great unsolved puzzle. The search for a single, unified theory, a theory of everything. Then, in the late 60s, a few physicists stumbled on a radical idea. What if the fundamental building blocks weren't zero-dimensional points, like tiny dots? What if they were one-dimensional strings, like unimaginably small loops or strands of energy? That was the birth of string theory. In that view, an electron isn't a point. It's a string vibrating in one specific pattern. A quark is the same string, vibrating differently. A photon of light is another vibration. Every particle, everything that makes up matter or carries a force, becomes a different musical note on this microscopic string. It was an astonishingly elegant idea. It promised to describe all forces and matter under one roof. But when they worked out the math for these vibrating strings, they hit a wall. The equations only made sense, they only stayed consistent, without those catastrophic infinities under one bizarre condition. The universe couldn't have just the four dimensions we know. Three of space, one of time, it needed more, the math demanded it. At first, the number that came out was 26 dimensions, which later got refined to 10. These extra dimensions weren't a feature they wanted. They were a requirement. The theory was confessing that for its symphony of vibrations to be in tune, the stage itself had to be far bigger and stranger than anyone had seen. So the hunt changed. It was no longer just for a theory of everything. It became a hunt for the missing architecture of reality. Dimensions that had to be there, woven into the fabric of everything. The equations were just stubborn. They wouldn't work in 3 dimensions of space and 1 of time. You'd try to calculate how a quantum string vibrates, how it interacts, and the math would give you impossible answers. It predicted particles with negative probabilities, which is meaningless, an event with less than 0 chance of happening. It also predicted tachyons, particles that would travel faster than light from the moment they were created. That breaks relativity, so the theory was saying the stage was too small. To make the symphony work, to avoid paradox, the universe needed a bigger backstage. For the earliest version, bosonic string theory, that meant 26 dimensions. That version had problems though. It didn't include the particles that make up matter. But the more complete framework, superstring theory, which wove together matter and force particles, that one found its balance in 10 dimensions. 9 of space, 1 of time. Later, there was a proposal called M-theory that suggested everything might fit in 11 dimensions. This number, it's not a guess. Physicists didn't choose it because it sounded interesting. It's the only number that makes the equations consistent, stable, mathematically beautiful. The extra dimensions are like load-bearing walls. Take them out, and the whole structure of string theory collapses. It becomes nonsense, so you have this trade-off. To unify all the forces of nature into one coherent framework, you have to accept that reality is richer, stranger than what our senses report, and that creates a puzzle, an immediate one. If these extra dimensions are mandatory, why can't we see them? Why don't we feel them? Where in our three-dimensional world could they possibly be hiding? We move through 3 dimensions of space, but the theory says there are more, 6 or 7 others. And that's the puzzle. If they're part of the universe, why does everything feel flat? Why just 3? The solution is something called compactification. That idea actually goes back to the 1920s. 2 physicists, Kaluza and Klein, were working on gravity and electromagnetism. They suggested a 5th dimension. One that was curled up, too small to see. Their work faded for a time, but it's the foundation now. So the extra dimensions aren't gone. They're just unbelievably tiny. Think of a garden hose. From far away, it's a line, 1 dimension. But if you're an ant on that hose, you have 2 ways to go. You can walk along the length. That's the big, visible dimension, or you could walk around the hose. A tiny circle. That second direction is always there. It's just compact. So small it vanishes at a distance. And that's what's proposed for our universe. The extra dimensions are curled up, compactified at the scale of the Planck length, 10 to the negative 35th meters. To give a sense of scale, if an atom were as big as our solar system, the Planck length would be about the height of a tree. It's a scale where space and time, our ideas, might break down. And these curled-up dimensions aren't somewhere else. They're here, at every point. Anywhere you look, the tip of your finger, the center of a star, at each location, there's the space we know, and also this hidden, tiny geometry. It's a striking thought. That woven into every inch of reality is this minute, complex shape. And that shape, the geometry of these hidden dimensions, it isn't minor. It decides everything. The shape of these extra dimensions isn't just random, it's a precise geometric lock, and the key is our physical laws. That shape is called a Kalabi-Yau Manifold. Named for 2 mathematicians, Eugenio Calabi and Xing-Tung Yau. These are 6-dimensional objects. They're incredibly complex. They're not simple spheres or loops. They're intricate. They have multiple holes. They twist and fold in on themselves. It's hard for our 3-dimensional minds to picture. Think of an ornate snowflake. But instead of 6-fold symmetry in a flat plane, it has symmetry in 6 dimensions, with tunnels, with voids weaving through its form. The equations of string theory require this. The extra dimensions have to take this specific shape. It's the only geometry that lets the strings vibrate consistently. That produces the stable particles we know. The stable forces. Without this exact structure, the theory falls apart. So at every point in space, in this view, there isn't emptiness. There's this minuscule 6-dimensional sculpture. A hidden landscape. Unimaginable intricacy repeating everywhere, and the specific form of that sculpture, its topology. The number of holes, the way it curves, that isn't just decoration. It's everything. It acts like a cosmic tuning board. The vibrations of a string depend entirely on the shape of the space it's in. Change the number of holes in the Kalabi-Yau manifold, and you change the resonant notes. You get a different set of particles, different masses, different charges, different forces with different strengths. So the particular Kalabi-Yau shape in our universe, that would be the reason. The reason we have exactly 3 families of matter particles. The reason gravity is so weak compared to electromagnetism. The reason for the constants that define reality. Exploring these shapes isn't like mapping territory. It's more like decoding fundamental source code. The cosmos's source code. It suggests a profound idea. That the laws of physics aren't written on some abstract tablet. They're etched into the geometry of hidden space. So the search for a theory of everything becomes, in part, a search for the one true shape. The correct Kalabi-Yau manifold. out of a staggering number of possibilities, and that leads to a monumental question. A troubling question, really, about the nature of our universe itself. There's another possibility, a second hidden landscape. It completely reimagines where those extra dimensions could be. In some versions of string theory, our entire universe is a three-dimensional island. A slice of reality. Physicists call that a brane, short for membrane. Picture a vast, flat sheet. That sheet is our home. All the matter we know, all the particles that make up stars and planets and us, they're stuck on this brane. They can't leave, but this brane isn't floating in nothing. It exists inside a higher dimensional space. That space is called the bulk. And in this bulk, the extra dimensions aren't necessarily tiny. They could be enormous, vast, unseen realms. Our three-dimensional universe is just one slice, one surface embedded in a much grander, hidden architecture. That's the brane world scenario, and it leads to a startling idea about gravity. In this model, the particles of matter and the carriers of forces like electromagnetism, they're like open strings. Their ends are pinned to our brane, they can't escape. But gravity is different. It's carried by closed loops of string. Think of a tiny lasso. These loops have no ends to tie them down. So they can drift off our brane. They can leak into the bulk, spreading out into those larger extra dimensions. If that's true, it offers an elegant answer. A long-standing mystery. Why is gravity so incredibly weak? A small magnet can lift a paperclip, defying the gravitational pull of the entire Earth. In the brane world view, gravity isn't inherently feeble. It just appears that way to us because most of its influence is bleeding away, dissipating into the hidden bulk. Its strength is diluted across dimensions we cannot access. Our perception of gravity is like hearing a shout from another room. The sound is muffled, not because the voice is weak, but because the walls are soaking up the energy. This shifts the search. Profoundly, we're no longer looking only for dimensions curled up at the Planck scale. We might be surrounded by dimensions that are, in fact, macroscopic. They could be as large as a millimeter or even bigger. Suddenly, the hidden layers of reality aren't just microscopic. They could be room-sized or cosmic. And if that's the case, how could we ever find evidence? Evidence of a world that exists literally all around us, yet remains completely invisible. The true power here is how it weaves together what we think of as separate threads. For a long time, physics has worked with four fundamental forces. Each one has its own rulebook. Gravity shapes the cosmos. Electromagnetism binds atoms and gives us light. The strong nuclear force holds atomic nuclei together. The weak nuclear force drives radioactive decay. They seem completely distinct. But if string theory is correct, they're not separate at all. They're different melodies played on the same instrument. The hidden dimensions are the instrument's body. Its shape defines every possible note. In the compactified geometry of a Kalabi-Yau manifold, a string vibrating in one specific pattern through all 10 dimensions emerges into our familiar 4 as a particle of light, a photon. That vibration carries the electromagnetic force. A different, more complex vibration through that same hidden landscape might emerge as a gluon, which carries the strong nuclear force that holds quarks together. And then there's gravity. In this symphony, gravity's carrier, the hypothetical graviton, is just another vibrational mode of the string, a closed loop vibrating in a particular harmony. That's the profound promise. All forces, from the cosmic pull of a galaxy to the bond inside an atom, come from the same fundamental object, a tiny string. Their differences aren't in substance but in rhythm. The geometry of the hidden dimensions acts as the ultimate tuning board. It decides which vibrations are possible. And it dictates how strongly those vibrations interact with each other. In our world, we measure this as coupling constants, the numerical strengths of the forces. Why is electromagnetism so much stronger than gravity? Why does the strong force have its specific power? According to this view, the answers are etched into the folds and holes of that 6-dimensional shape existing at every point. So the quest to unify the forces transforms into a geometric puzzle. It's not about finding a single mathematical equation for all forces. It's about discovering the one true shape of hidden space, whose vibrational spectrum perfectly mirrors the particle zoo and force strengths we observe. This geometric unification suggests something almost philosophical. The laws of physics aren't arbitrary rules imposed on the universe. They're a direct consequence of space's hidden anatomy. The shape of reality dictates its behavior. So when we ask why the universe is the way it is, string theory points us toward a silent, intricate geometry, curled up into a realm forever beyond our sight, yet responsible for everything we see. This geometric puzzle has a scale that's almost overwhelming. It's not just a few possible shapes for those hidden dimensions. The number of stable Kalabi-Yau manifolds is staggering. Physicists estimate it could be around 10 to the 500, a 1 with 500 zeros after it. A number so vast it dwarfs the count of atoms in the observable universe. So it's not a short list of options, it's a landscape, an endless, rolling terrain of possible realities. And that's where the implications become truly cosmic. Because each distinct shape in that landscape, each unique way the extra dimensions could curl up, doesn't just tweak a physical constant. It defines an entire universe, a universe with its own set of particles, its own force strengths, its own laws. In one pocket of this landscape, the hidden dimensions might curl into a shape that makes gravity strong and electromagnetism weak. Stars in that universe would burn out in a flash. In another pocket, a different geometry might not allow atoms to form at all. So our universe, with its specific, life-permitting parameters, would be just one bubble. One possibility that actually unfolded. We'd inhabit a single, fortunate valley in a colossal, mostly uninhabitable multiverse. Those hidden dimensions become more than a feature of our reality. They become the master key to a cosmic diversity beyond all human comprehension. And this landscape idea tackles one of the deepest mysteries in science. Why does our universe seem so finely tuned for life? If gravity were slightly different, or the mass of the electron altered by a fraction, stars wouldn't form, chemistry would be impossible, life could not arise. It feels like a cosmic coincidence. The string theory landscape offers a radical answer. It suggests every possible tuning exists somewhere. In the vastness of the multiverse, every conceivable set of physical laws is realized in some bubble universe. So we don't live in a universe that was magically fine-tuned. We simply find ourselves in one of the rare bubbles where the hidden dimensions curled up in just the right way to produce stable atoms, long-lived stars, and the complex chemistry that leads to us. This doesn't explain why our particular geometry was chosen. It shifts the question entirely. We stop asking, why do we have these specific constants? Instead, we ask, which hidden geometry do we actually inhabit? Our search for the fundamental laws transforms. It becomes a cosmic census, an attempt to map our local valley in an infinite landscape of possibilities. It means the architecture of our reality, defined by those silent, curled-up dimensions, might be both unique and utterly common. A single note in an endless symphony of universes. A theory that tries to describe everything has to leave some kind of trace, something we could find. The problem with string theory is the scale. The energy to actually see a string is far beyond anything we can reach. But those extra dimensions, the hidden ones, they might give us a backdoor. A way to test it indirectly. Because if they're real, they should change the rules of physics in small ways. Ways we might be able to see, especially in the most violent collisions we can make. Like at the Large Hadron Collider. In those rings underground, protons are smashed together almost at light speed. They recreate conditions just after the Big Bang. And in those flashes of energy, the hidden architecture of space might show itself. For a moment, one prediction is about gravity. In the Brane world idea, where gravity can leak into large extra dimensions, its true strength might only show up at incredibly tiny distances. At the scales the collider probes, Gravity could become as strong as the other forces. And if you focus enough energy into a tiny enough space, you could, in theory, tie space-time into a knot. You could make a microscopic black hole, not the kind that eats stars, a quantum-sized one. It would evaporate almost instantly in a burst of particles. The pattern of that explosion would be a clear signal, a signature of gravity working in more than 3 dimensions. So far, the detectors haven't seen that. But the search keeps going at higher energies. Another possible fingerprint comes from vibration, because every particle is a note on a string. In a universe with curled-up dimensions, a string can vibrate in more complex ways. It has a simple, fundamental note that's our familiar electron or quark, but it can also vibrate with higher harmonics, like pressing a guitar string to get a sharper pitch. In the hidden dimensions, these higher vibrations would show up in our world as heavier, duplicate versions of particles we know. Physicists call them Kaluza-Klein states. They'd be like shadow particles, same charge as an electron but much heavier. If there's enough energy in a collision, a string could be excited into one of these higher states. And for an instant, a heavy twin of a known particle would flash into existence before it decayed. Detectors would see a sudden disappearance of energy, or a spray of unusual particles that don't fit the standard catalog. These are the anomalies teams at the collider look for, with immense care. No definitive evidence has come up. But each new run of the machine, each increase in energy, probes deeper into the territory where these geometric effects might be. This search changes string theory. It moves it from a mathematical marvel to something with a foothold in experiment. It moves the question from, is it beautiful, to, is it true? The silence so far isn't a dismissal. It's a map of where the hidden dimensions are not. And with every possibility excluded, the landscape of potential realities gets a little more focused. The experimenters are like cosmic cartographers, not mapping stars, mapping the invisible folds of space itself. Gravitational waves are more than cosmic tremors. They could be messengers from the hidden architecture of space. When 2 black holes spiral together and merge, they shake the fabric of spacetime. They send out ripples that travel across the universe at the speed of light. These waves are incredibly faint by the time they reach us, but we can detect them now with observatories like LIGO and Virgo. According to general relativity, these ripples have only 2 possible polarizations. 2 ways they can wiggle space as they pass. It's like a wave on a pond that can only move up and down or side to side. But string theory suggests something different, especially in Brane world scenarios. If gravity can leak into a larger bulk of extra dimensions, then gravitational waves might travel through that hidden realm. They could take shortcuts, or they could develop extra modes of vibration, additional polarizations that our 4-dimensional physics doesn't allow. It would be as if a wave on a pond could also twist the water in a spiral motion. Our current detectors aren't yet sensitive enough to spot these subtle differences, but future observatories in space might be. A single, precise measurement of a gravitational wave from a cataclysmic event, showing a pattern that defies Einstein's pure predictions, could be the first indirect evidence. A whisper from the bulk, a clue that the waves are traveling through more dimensions than we see. There is another, even older cosmic signal, the cosmic microwave background radiation. This is the faint glow left over from the Big Bang itself, a snapshot of the infant universe when it was just a hot, dense soup of particles and energy. This afterglow fills the entire sky, and etched into its subtle temperature variations could be the imprint of the universe's very first moments, a time when all dimensions, the familiar and the hidden, may have been on equal footing. In those first instants, the extra dimensions would have been dynamic, vibrating or evolving. As the universe expanded and cooled, they would have compactified, snapping into their tiny, stable shapes. That dramatic process, that settling of the cosmic geometry, would have sent shockwaves through the primordial plasma. Those tremors could have left faint scars in the pattern of the microwave background. Specific statistical anomalies, or unexpected correlations in the polarization of this ancient light, could point back to a higher dimensional birth. Scientists are analyzing data from telescopes like Planck, searching for any pattern that doesn't fit the standard four-dimensional model of cosmic inflation. They are looking for a fossil, a geometric fossil from a time when the full 10-dimensional symmetry of string theory might have been manifest. The search is painstaking because the signals would be incredibly subtle, buried under eons of cosmic evolution. But if found, it would be a direct line to the universe's hidden blueprint. These two approaches, listening to the crashes of black holes and reading the oldest light in existence, turn the entire cosmos into a laboratory. We are no longer limited to what we can build on Earth. The universe is performing the most energetic experiments for us, and we are learning to read the results. The silence so far is not empty. It is a map of what is not there, guiding us toward what might be. Every non-detection refines the theory. It tells us which shapes in the vast landscape are less likely, which hidden geometries our universe probably did not choose. This is how science closes in on truth, by listening to the cosmos with ever more sensitive ears, waiting for it to reveal the dimensions it has kept secret since the beginning. This search for hidden geometry isn't just curiosity. It could solve one of the most stubborn mysteries in science, the hierarchy problem. It's a simple question. Why is gravity so incredibly weak? A little fridge magnet can beat the gravity of the whole planet. The difference in strength between gravity and electromagnetism is a factor of 10 to the 36. That's 36 zeros. It's not a small gap. It's a cosmic chasm, and it seems like a bizarre accident. In our standard model, there's no reason for it. It's just a number we plug in, a constant. But nature doesn't usually leave something that big unexplained. This is where the hidden dimensions give an answer. An almost too elegant answer. In the Brane world picture, gravity's true strength might not be weak at all. It could be as strong as the other forces. But we feel it as feeble because it's the only force that can leak. Matter and light are pinned to our three-dimensional brain, but gravity, carried by closed strings, can spread out into the larger bulk. Into those vast extra dimensions. Think of a light bulb. Put it in a small room, the space is brightly lit. The light is concentrated. Now take that same bulb and hang it in a massive warehouse. The light spreads out in all directions, filling the huge volume. From any one spot, the light seems dim. Diluted, that's gravity in the Brane world. Its strength isn't weak. It's just diluted, spread across a hidden spatial architecture we can't perceive. The force we feel is just the tiny fraction left on our slice of reality. This is a profound shift. It solves the hierarchy problem not by inventing new particles or magical fine-tuning, but through geometry. A reimagining of spacetime itself. The weakness of gravity becomes a clue, a footprint, evidence we're living on an island in a higher dimensional sea. This possibility gives the search a real urgency. It's not just about completing a beautiful mathematical theory. It's about finding a natural explanation for a fundamental feature of our world, one that's baffled physicists for generations. If the architecture of hidden space can answer a question this deep, it forces us to listen, to take the idea seriously. Because the solution might have been hiding in plain sight, woven into the fabric of the universe all along. The biggest mysteries in the universe might have their answers in those hidden folds. We know most of the cosmos is made of things we can't see. Dark matter, dark energy. Together, they are about 95% of everything. We see what they do. Dark matter's gravity holds galaxies together. Dark energy is pushing everything apart, faster and faster, but we don't know what they are. They're like shadows on the wall. And string theory, with its extra dimensions, gives those shadows a new place to hide, or even to come from. Some ideas say dark matter isn't made of particles like ours at all. It could be made of particles that are stuck, not on our brain but in the bulk. In those larger, hidden dimensions, those particles would feel gravity, so they'd clump and shape the galaxies, but they'd be completely invisible to light. To all the other forces, they'd be ghosts moving through the walls of our reality, only showing themselves by their pull. Another thought is that dark matter particles are right here, but they are different vibrational states of the string. Notes that aren't part of the standard symphony. They could be tied to the specific geometry of the Calabi-Yau shape. A particular fold or hole in that tiny space might produce a stable, heavy vibration. A particle that hardly interacts with anything except through gravity. It's a compelling idea that the missing mass of the universe could come from the hidden architecture of space itself. Then there's dark energy, the force pushing the cosmos apart. What if that push isn't a new force? What if it's the hidden dimensions slowly changing? Over cosmic time, the compactified geometry might be trying to shift. To decompactify just a little, or to settle into a slightly different shape. That tiny adjustment in the fabric of reality, happening everywhere at once, would inject energy into space. It would look exactly like a repulsive force, making galaxies fly apart. So dark energy might not be a mysterious substance. It could be the latent energy of the extra dimensions. Aside from the compactified geometry as the universe gets older. These are speculations for now, beautiful possibilities, but they show the power of the framework. By adding these hidden layers, string theory doesn't just explain the 5% we see. It creates a whole playground for thinking about the 95% we don't. It tries to unify the known and the unknown under one geometric roof. The shadows of the cosmos might not be separate mysteries. They could be different faces of the same hidden reality. A reality whose full dimensions we're only starting to sense. Our own minds are the final frontier. We are three-dimensional creatures. Our senses, our tools, our instincts, they are all built for a world of length, width, and height. The idea of 6 more spatial directions, our neurology can't process it. It's a wall. You can't close your eyes and picture a Kalabi-Yau manifold, not really. What you might get is a 3-dimensional shadow. A crude analogy for something far more complex. That's the core challenge. String theory asks us to accept a reality described not by pictures, but by mathematics. Cold, clean logic. To understand it, we have to see with equations. Mathematicians use projections. Think of a complicated sculpture. You shine a light on it, the shadow on the wall is a flat silhouette. That 2-dimensional shadow hints at the form, but loses the depth, the interior structure. Now imagine that sculpture exists in 6 dimensions. The 3-dimensional shape we can sketch is just its shadow. A feeble glimpse. Our entire universe, 3 of space, 1 of time, might itself be a projection, a cosmic shadow, cast by the vibrations of strings playing out on a 10-dimensional stage. This means letting go of a fundamental desire, the desire to visualize, to have a mental movie of how it all works. Instead, we follow the mathematical narrative. The equations tell a story of consistency and beauty, of vibrational harmonies that only make sense if the stage has a specific, intricate architecture. This cognitive leap is immense. It requires trust in a form of reasoning that transcends our biological limits. And in that difficulty, there's a strange beauty. It suggests the universe isn't built for our convenience. Its deepest truths aren't meant to be seen with our eyes, but understood with our minds. The structure of reality is written in a geometric language we're only beginning to decipher. A language that operates in silent dimensions, forever beyond our direct perception. We can't see this geometric reality, and that forces a question about perception. Our whole experience of the cosmos is built on 4 dimensions: length, width, depth, and time. We trust that as the complete stage. But if string theory is right, it's only a slice. A fragment of something much richer. A multi-dimensional construct. We're interpreting the universe through a keyhole, believing the sliver of light we see is the whole room. That idea connects to an old story. Plato's allegory of the cave. Prisoners, chained from birth, only see shadows on a wall, cast by objects moving behind them. They believe those shadows are all of reality. One prisoner escapes, sees the true forms, the fire, the wider world. He goes back to tell the others. They don't believe him, they think it's madness. Our situation might be similar. The three-dimensional world we navigate, the forces we measure, could be the shadows cast by the true forms, which would be vibrating strings, dancing in a 10-dimensional geometry. The cave is our limitation. We're biologically bound to perceive only the projection. The shadows feel solid, real, undeniable, but they point to a source we can't witness directly. This isn't just a metaphor about ignorance, it's a concrete challenge to evidence. Science is built on observation, measurement, testable prediction. But what happens when the most fundamental parts of reality are hidden by their very nature? If these extra dimensions are curled up at the Planck scale, or if we're confined to a brain, they're beyond any microscope or telescope we could ever build. So how do we confirm something exists if we can never see it, touch it, interact with it directly? We're left with footprints, ripples in the pond of our observable reality. A missing energy signature in a particle collision, an anomalous polarization in a gravitational wave, a statistical quirk in the cosmic microwave background. These would be the shadows of the shadows, indirect, second-order evidence that creates a tension at the heart of modern physics. On one side, there's mathematical elegance, internal consistency, a beautiful, unified story that explains a lot. On the other side, there's the rigorous demand for proof. The story may be compelling, but is it true? It pushes the boundaries of what we consider knowable. It asks us to expand our definition of evidence, to accept that the deepest architecture of the universe might only reveal itself through subtle, consistent effects on the world we can measure. It's a humbling reminder. Reality is under no obligation to be fully comprehensible to the human mind, or accessible to human tools. Our quest becomes a delicate dance. We follow the mathematics into unseen realms, then we search our own world for the faintest echoes of their existence. We're listening for a whisper from a hidden room, knowing we may never open the door. The idea of hidden dimensions seems like a modern thought, but it started much earlier. In 1921, a physicist named Theodore Kaluza did something with the math. He took Einstein's equations for gravity, for four-dimensional spacetime, and rewrote them for 5 dimensions. He added one more spatial dimension, and when he did the math, something happened. The equations split. One part was Einstein's gravity in our 4 dimensions. The other part, coming from the geometry of that 5th dimension, matched Maxwell's equations for electromagnetism. So gravity and light, the 2 known forces, came out of a single 5-dimensional geometry. Unification through geometry, a hidden dimension as a bridge, but then there was a question: if there's a 5th dimension, where is it? Why can't we see it? A few years later, Oscar Klein had an answer. He said this extra dimension wasn't large, it was curled up, compactified into a tiny circle, so small we could never detect it. A particle moving in that tiny loop would look to us like a point with an electric charge. Its momentum around the circle would appear as charge. That was Kaluza-Klein theory. The laws of physics we see could be a consequence of the shape of hidden space. It was an elegant idea. It captivated people for a while, a beautiful geometric vision. But it ran into problems. It couldn't easily fit the new rules of quantum mechanics. It predicted a particle that wasn't found, and as quantum field theory grew, this 5-dimensional idea was set aside. It became a historical footnote. Then decades passed. Physicists working on string theory hit a paradox. Their equations only made sense in more dimensions. Many more. And the answer to where those dimensions were was exactly what Klein said: compactification. String theory took that old idea and consumed it. That single curled-up dimension became 6 or 7, curled into complex shapes called Kalabi-Yau manifolds. The goal wasn't just to unify gravity and electromagnetism anymore. It was to unify all forces, all matter. The old framework was a sketch. String theory was trying to build the cathedral, so this history matters. It shows the concept of hidden dimensions isn't just a wild guess. It's a recurring theme. It comes up when you push for greater unity in how you describe the cosmos. Kaluza and Klein had a first glimpse of a principle. That the architecture of space, including the parts we can't see, might dictate the laws of nature. Their forgotten theory was a precursor, a whisper of what came later. It shows that new paradigms often grow from old, abandoned ideas, waiting for their moment. Supersymmetry is this elegant mathematical dance. It's what makes the whole framework possible. It's a profound balance. In our universe, you have two fundamental classes of particles. Fermions, like electrons and quarks, they're the building blocks of matter. They're solitary, they resist being in the same state. Then you have bosons like photons and gluons. They're the force carriers, they're social. They pile on top of each other. They seem completely different. But supersymmetry proposes that for every known fermion, there's a bosonic partner. And for every known boson, a fermionic partner. So the electron gets a partner called the selectron. The photon gets a partner called the photino. It's a grand doubling of the particle catalog. And this isn't just for symmetry's sake. It's a mathematical lifeline for string theory. When physicists tried to build a universe with vibrating strings, the equations were plagued with inconsistencies. The hidden dimensions were unstable. They'd either want to collapse to a point or balloon out to infinity. You'd get a universe that couldn't support life as we know it. Supersymmetry acts as a stabilizing force. It introduces a perfect tension, a cancellation between the quantum jitters of matter particles and force particles. That tension pins the geometry of the curled-up dimensions in place. It freezes the Kalabi-Yau manifold into a specific, stable shape. Without supersymmetry, the hidden architecture would be a house of cards, collapsing under its own quantum fluctuations. So this symmetry isn't an optional feature. It's the glue. It holds the entire higher dimensional edifice together. The stability of our very reality in this view depends on a symmetry we have never directly seen, and that creates a powerful prediction. If string theory is correct and the hidden dimensions are stable, then supersymmetry must be a feature of nature. Those partner particles must exist. Our failure to find them so far at particle colliders is one of the great puzzles. It could mean they're much heavier than expected, requiring more energy to create. Or it could mean our understanding of how supersymmetry is broken is incomplete, how the perfect symmetry is hidden from us at everyday energies. Yet the theoretical necessity remains. The requirements of the hidden geometry reach out. They impose conditions on the world we can observe. They tell us our particle zoo should have a shadow zoo. This is a stunning example of how the search for a unified theory works. You start with a mathematical structure, strings in higher dimensions. To make that structure consistent and stable, you're forced to add elements, like supersymmetry. And those elements then make testable predictions about our own world. We're reverse engineering the universe's blueprint by following the demands of mathematical consistency. The silence of our detectors isn't a dismissal. It's a clue. It tells us that if the hidden dimensions are real, they're stabilized in a way that keeps their supersymmetric guardians just out of our current reach, waiting for a more powerful collision to reveal their presence. String theory has a kind of mathematical elegance, but it's not the only path forward. There's another framework. It asks us to look at space and time from a completely different angle. Loop quantum gravity. This doesn't start with strings. It doesn't start with extra dimensions. It starts with a radical idea that space itself isn't smooth. It isn't continuous the way Einstein described it. Instead, it's woven from tiny loops, finite loops. They form a network, a spin network. And the geometry of space, the three dimensions we know, it all emerges from how these loops connect. The fabric of reality is like a tapestry. The loops are the individual threads. Their interweaving creates the space we experience. It's a background-independent theory. There's no pre-existing stage. The stage is built from the relationships between these fundamental loops, and it all happens here, in the familiar arena. 3 spatial dimensions, 1 of time, no hidden, curled-up realms are needed. The contrast with string theory is striking. One unifies by adding dimensions. By adding vibrating strings, the other quantizes by rethinking the geometry of the dimensions we already have. It's a fundamental fork in the road, and it shows something. The necessity of hidden dimensions, that's not a universal demand of nature. It's a specific requirement. It comes from string theory's particular mathematical melody. The extra dimensions are the price of admission for that symphony. For loop quantum gravity, the music is composed entirely within the concert hall we know. This divergence isn't a weakness, it's a sign of vitality. When you face a mystery this deep, multiple profound answers can emerge. Each framework follows its own internal logic. To a breathtaking conclusion, one paints a universe of hidden, intricate geometry. The other depicts a universe of discrete, woven connections. They're both trying to answer the same cosmic question. But they start from different premises, they build different worlds, and that forces a humbling realization. The hidden dimensions we've been exploring, they're not an inevitable feature of reality. They're a compelling possibility, born from one of the most beautiful mathematical structures ever conceived. Their existence is a prediction, waiting for a whisper of confirmation from the cosmos. Whether that whisper ever comes, that will determine which of these visions, if either, is the true story. The holographic principle is a startling idea from geometry. It says the universe isn't what it seems, like a credit card hologram, a flat sticker that creates the illusion of a 3D object. All the information for that 3D image is encoded on the 2D surface. Now apply that to the cosmos. Some versions of string theory, through something called the AD-SCFT correspondence, propose something similar. That a description of a volume of space, with gravity with all its hidden dimensions, can be perfectly equivalent to a description of quantum physics without gravity, living only on the boundary of that space. The boundary is 1 dimension lower. So a 3-dimensional world like ours, with its curled-up extra dimensions, could be a holographic projection. A cosmic illusion from information painted on a distant, 2-dimensional surface. In this view, the 3 dimensions we move through, the solidity we feel, that's not the fundamental reality. It's a translation, a rendering. The true, fundamental description might be written on a lower dimensional screen at the edge of everything. This isn't just a metaphor. It's a precise mathematical equivalence discovered by physicist Juan Maldacena. It's a powerful tool. It lets you translate incredibly difficult calculations about gravity in a higher dimensional space into more manageable calculations about quantum particles on a surface. But the philosophical implications are staggering. It blurs the line between what's real and what's a projection. The hidden dimensions, the force of gravity, the fabric of space-time within the volume, all of it emerges from chaotic quantum interactions on a lower dimensional boundary. You and I, everything we see, would be a hologram, a rich, interactive, 3-dimensional experience generated from a vast, swirling sea of quantum information on a distant surface. This idea redefines where reality truly resides. It suggests the most complete description of our universe might not be found within it, but on its skin. On a membrane of information, from which everything else, including the hidden dimensions we've been searching for, is projected into being. The barrier is a number, an energy scale. To actually see a string, to probe those tiny curled dimensions, you'd need to reach the Planck energy. It's an unimaginable magnitude. Roughly 10 to the 19th times the mass energy of a single proton. To get there with a collider, you'd need a machine the size of a galaxy, or one that uses more power than our whole civilization produces in a century. Our best tool, the Large Hadron Collider, operates at energies that are, by comparison, a gentle breeze against a mountain. It's not an engineering problem. It's a fundamental gap between what we can do and the bedrock of reality. Those hidden dimensions, if they're curled at the Planck scale, are shielded by this energetic fortress. Our probes just bounce off the outer walls. They never touch the geometry inside. Now, for the Brane world idea, where dimensions could be larger, the energy needed drops. But it's still colossal. It might need a collider hundreds of times more powerful than the LHC. A machine spanning a continent. The energy to create those heavy shadow particles, the Kaluza-Klein states, or to tie space into a microscopic black hole, stays just beyond our reach. That's the conundrum. The theory paints this vivid picture of hidden architecture, but puts it behind a veil we can't lift with our tools. It forces string theory into a kind of suspended state. A mathematical prophecy waiting for a technological revolution. This energy gap isn't a flaw in the theory. It's a lesson in cosmic scale. It tells us the universe's deepest secrets aren't kept in distant galaxies. They are in realms of energy so extreme they defy our everyday intuition. We're like deep-sea creatures in the abyss, trying to understand fire. We have descriptions, equations that model its behavior, but we can't create the conditions to see it burn. Our entire civilization, with all its colliders and telescopes, operates in the cool, low-energy aftermath of the Big Bang. We're studying the embers, trying to deduce the inferno. And the architecture of hidden space was forged in that inferno. So we look for the faintest cooling patterns in the embers. The subtle statistical anomalies, the missing energy, the whispers in gravitational waves. These are our only clues. The energy scale conundrum means that for the foreseeable future, we may only ever know these extra dimensions indirectly. Through their shadows, through the subtle ways they bend the rules of the world we can see. It's a testament to the human mind that we can even conceive of such hidden realms. That we can describe them with mathematics, while our physical reach falls so profoundly short. The reliance on mathematical elegance leads to a debate. If the hidden dimensions are beyond our direct reach, how do we know they're real? It's a question of falsifiability. For a scientific idea to be accepted, it has to be testable. It has to make predictions that could be proven wrong. Critics say string theory fails that test, with its landscape of possible vacuum states, 10 to the 500 possible shapes. The theory can accommodate almost any observational outcome. And if you can explain everything, you've explained nothing. It becomes a beautiful piece of mathematics, but not necessarily a description of our physical world. The energy scales, the hidden geometries, place it in a realm that might be forever beyond experimental proof. That's a serious charge. It questions whether decades of work have been a detour. A fascinating intellectual exercise, but not science in the traditional sense. The response from proponents is profound. They point to history. There are moments when pure mathematical beauty has been a startlingly accurate guide. In the late 1920s, Paul Dirac sought an equation for the electron consistent with quantum mechanics and special relativity. The math he derived was elegant. Symmetrical, but it had a strange feature. It demanded a particle with the same mass as the electron but opposite charge, a mirror particle. At the time, no such thing was known. It seemed like a mathematical artifact, an oddity, but Dirac trusted the equation's beauty. He proposed the positron, and a few years later, it was discovered in cosmic rays. Antimatter was real. The mathematical compass had pointed true. String theorists argue we're in a similar moment. The mathematical structure of string theory, its requirement for extra dimensions, its inherent supersymmetry, its natural inclusion of gravity, is too compelling, too uniquely consistent to be ignored. It solves problems that have resisted every other approach. In the absence of a galaxy-sized collider, they suggest this internal coherence, this explanatory power, is itself a form of evidence. It's a different kind of science. You follow the logic of the equations into unseen realms, trusting their consistency mirrors a consistency in nature. This debate cuts to the heart of how we understand the universe. Is science solely about prediction and testability? Or is the search for a complete, consistent, and beautiful description also a valid path? When our tools cannot reach the bedrock, do we stop digging? Or do we use the maps drawn by mathematics, knowing they've led to discoveries before? This isn't just about strings and hidden dimensions, it's a philosophical rift. It defines our current era of fundamental physics. It asks what we accept as truth when the cosmos hides its deepest blueprints behind an impassable veil. The debate in mathematics isn't a dead end, it's a call to action. It forces us to build better eyes, to listen with sharper ears. Since we can't reach the energy of that hidden realm, we have to become masters of precision. We have to learn to read the faintest signatures it leaves on our own world. The next experiments won't smash protons with galactic force. They'll hunt for whispers, for the subtlest tremors in the fabric of our reality. The hunt is becoming multi-pronged, using every tool from the cosmic to the quantum. On the particle frontier, plans are already drawn for machines that dwarf our current ones. The proposed future circular collider, a ring over 50 miles in circumference, buried deep under the European countryside. It would be a staggering leap. It wouldn't reach the Planck scale, but it would push energies far beyond today's limits. In its collisions, physicists would search for more than black hole signatures or heavy partner particles. They'd look for delicate statistical anomalies, patterns in the debris that ever so slightly favor a model with extra dimensions over the standard one. It's detective work, sifting through quintillions of events for a single, consistent clue. But the search isn't only about brute force, it's also about exquisite sensitivity. Imagine measuring the gravitational pull between two tiny gold spheres, smaller than a grain of sand, separated by a hair's width. At these microscopic distances, if there are large extra dimensions, gravity's behavior should change. It should become slightly stronger as you probe scales where its lines of force can't spread into the bulk as easily. Experiments like this are running now in quiet labs. They use advanced lasers and cryogenic temperatures to eliminate any vibration, any thermal noise. They're testing Newton's law of gravity at distances smaller than the width of a human cell. A deviation here, a tiny bump in the data, could be the first direct signal of a hidden macroscopic dimension. Our cosmic ears are also being upgraded. The next era of gravitational wave astronomy won't just listen from the ground. Space-based observatories, like the planned Laser Interferometer Space Antenna, will float in formation, millions of miles apart. They'll detect the low-frequency hum of merging supermassive black holes, events that shook the cosmos when galaxies were young. The pristine quality of these signals, traveling for billions of years, could reveal subtle distortions. If gravitational waves take shortcuts through the bulk, or if they carry extra vibrational modes from higher dimensional space, their waveform will be ever so slightly scrambled. It would be like hearing a perfect chord played on a piano, but with one note faintly out of tune because the sound traveled through a hidden room. Even on a tabletop, quantum ingenuity is at work. Scientists are using ultra-cold neutrons, which are exceptionally sensitive to the forces around them. By studying how these neutrons bounce between surfaces or how their quantum states evolve, researchers can probe for any extra interactions, any slight shifts that might be caused by the influence of particles or fields existing in the hidden dimensions. It's a search for phantom influences, for a gentle nudge from a realm we cannot see. And our view of the infant universe is about to get sharper than ever. Next-generation telescopes, like the James Webb Space Telescope and its successors, are reading the cosmic microwave background with unprecedented detail. They are mapping the polarization of this ancient light, looking for imprints of primordial gravitational waves. These waves are a direct probe of the universe's first moments, a time when all dimensions may have been unfurled. A specific, unexpected pattern in this data could be the fossilized echo of the extra dimensions compactifying, a snapshot of the hidden geometry freezing into place. This is the new phase of the hunt. It's no longer a single, monumental experiment, but a symphony of precision. from continent-sized colliders to exquisitely controlled tabletop sensors. From the silent depths of space to the quantum states of a single particle, every approach listens for a different part of the signal. The goal is to triangulate the truth, to find a whisper so consistent, so undeniable, that it points unequivocally to the hidden architecture woven into everything. The silence we hear now isn't emptiness. It's the quiet before a potential chorus of discovery. An ant crawls along a high-voltage power line. Its world is just that line. It can only go forward or back. To that ant, the universe has one spatial dimension. It doesn't know about the electrical pylons, or the landscape below, or the open sky. Those three-dimensional spaces are hidden. They are compactified from its view. The ant is stuck in a lower-dimensional slice of a much bigger reality. We're in a similar spot, but with an extra layer. We see 3 dimensions of space and 1 of time. We move along this 4-dimensional wire of our spacetime, thinking it's the whole stage. But if string theory is right, there are more dimensions. They're not far away. They're curled up, compactified into a tiny, intricate geometry at every single point we pass. Just like the ant can't see past its wire, we're blind to these hidden folds. They're woven into the fabric of every location, but they are beyond our senses and our instruments. This shows something about perception and reality. The ant's one-dimensional experience is real to it. The wire feels solid and complete, but that limited view keeps it from seeing the forces that actually shape its world. The cable's tension, the flow of electricity, the wind that moves it, all of that comes from the larger, hidden structure. In our universe, the strengths of the fundamental forces, the masses of particles, the laws of physics themselves, they could come from our own hidden architecture. The compactified dimensions aren't just passive scenery. They're the tuning board. They dictate the vibrational notes of strings, and those notes become everything we see and touch. We're like that ant, interpreting the shadows on our wall as the whole story. The true source of the light stays unseen, curled up in a geometry we're only starting to map with math. The fine-tuning of the hidden geometry is a real puzzle. Our universe's specific compactification seems improbably perfect. Change the strength of electromagnetism just a fraction, and atoms don't hold together. Make the cosmological constant slightly larger, and galaxies never form. And all these constants are tied to the shape of those curled-up dimensions. So why does our universe have the one shape that allows for stars and planets and life? In the vast landscape of possibilities, ours is an exceptionally rare valley. That leads to a radical line of reasoning, the Anthropic Principle. It feels unsettling. The suggestion is we're asking the question backwards. We shouldn't wonder why the hidden dimensions are tuned for life. We should recognize we can only ask the question in a universe where they are. In the colossal multiverse of string theory, every possible Calabi-Yau shape exists somewhere. Countless bubbles of reality, each with different physical laws. Most are barren, silent, no complex structure at all, but in a tiny fraction, the geometry vibrates in just the right harmony. Those rare bubbles can cook up atoms, ignite stars, and eventually give rise to observers. Observers who look up and wonder why their world seems so carefully arranged. The answer isn't a cosmic designer. It's a cosmic selection effect. We find ourselves in a habitable neighborhood for the same reason a fish finds itself in water. It couldn't find itself anywhere else. That shifts the entire goal of fundamental physics. Instead of seeking a single, unique prediction from the equations, we might be mapping a statistical distribution of possibilities within a multiverse. Our universe isn't the only possible outcome. It's simply a possible outcome that contains us, that places conscious observation in a strange new dialogue with cosmic structure. The universe's hidden architecture isn't fine-tuned for us. We are a consequence of its rare, habitable tuning, a biocentric answer to a geometric question. We are here because the silent, six-dimensional sculpture at every point allows it. And that realization becomes a clue. It tells us that if string theory's landscape is real, then our existence is a data point. Evidence that we inhabit one of the rare, lush islands in a vast and mostly inhospitable sea of realities. There's this dialogue between science and art. It points to a shared impulse. We look at a flat canvas and we see depth. We read about a two-dimensional world and we feel that ache for a third. The idea of hidden dimensions. It was a cultural fascination long before it became a requirement in string theory. Back in 1884, a schoolmaster named Edwin Abbott wrote a novella, Flatland. It's a geometric romance. The narrator is a square. He lives in a world of only two dimensions. He knows length and width. His society is rigid, built entirely on shapes and angles. Then he has a vision. A sphere from the third dimension visits him. It lifts him out of his plane, lets him see his world from above. And for the first time, he sees the insides of every locked room, the true shapes of his neighbors. It's a revelation. It shatters his entire understanding of reality. When he returns and tries to explain the third dimension, he's imprisoned for heresy. Flatland wasn't just a whimsical tale. It was a satire of Victorian social hierarchy. But its enduring power is the metaphor, the horror and wonder of discovering there's more to reality than your senses report. That a higher dimension isn't just a new direction, it's a new mode of perception, a place of ultimate perspective. That idea has echoed through stories ever since. In science fiction, hidden dimensions become gateways. In the film Interstellar, astronauts navigate a higher dimensional tesseract to communicate across time. It's portrayed not as a place you walk into, but as a labyrinth of folded space, where every moment in a room exists all at once. The narrative uses the dimension as a solution, but also as an emotional device. A father reaching through the architecture of the universe to connect with his daughter. Or in novels like Madeleine L'Engle's A Wrinkle in Time, characters tesser they wrinkle space to travel vast distances. The explanation is a bending through a fifth dimension, a shortcut. For the young protagonists, it's a terrifying, beautiful initiation into a cosmos far stranger than they ever dreamed. These stories take the abstract geometry of physics, and they give it narrative weight. They ask, what would it feel like to experience a higher dimension? The answer is often overwhelming. A flood of information, a loss of familiar boundaries, a godlike perspective that comes with profound loneliness. This cultural resonance points to something deeper. The hidden dimension works as a metaphor for the unseen layers of our own world. Psychologically, it can represent the unconscious, the vast, folded complexity of memories and drives that influence our conscious, three-dimensional lives. Socially, it can symbolize hidden structures, power, economics, digital networks shaping our reality from a realm we scarcely perceive. Technologically, our dive into virtual reality and AI feels like constructing new dimensions of experience. Layers of interaction superimposed on the physical world. When art explores these ideas, it does more than explain science. It prepares the imagination. It makes the mind flexible, ready to consider that reality might be built from more than what's evident. A physicist working on Kalabi-Yau manifolds and a writer describing a dimensional gateway, they are engaged in a similar act. They are both using the tools of their craft to model possibilities, to stretch the boundaries of the known. This cultural diffusion is a testament to the idea's power. It shows our quest to understand the universe isn't confined to equations. It lives in our stories, in our art, in our deepest metaphors for mystery and discovery. The hidden dimension, in the end, is more than a geometric necessity. It's a mirror, reflecting a conviction that there's always more to find, just beyond the edge of sight. We're at a crossroads, a place of real uncertainty. String theory says there have to be extra dimensions. It's a mathematical necessity, a piece of cosmic architecture that could solve everything. But right now, they are a ghost. No microscope sees them, no telescope catches their shadow, so the story goes one of two ways. It becomes a revolution or it becomes a lesson. One path, An experiment finds the evidence. Maybe the next particle collider, bigger than anything before, records a burst of energy. And that burst only makes sense if it's a microscopic black hole. A direct signal of gravity working in extra dimensions. Or a space-based gravitational wave observatory picks up a ripple with an impossible polarization. A whisper that traveled through the bulk. That single discovery would be seismic. It would validate decades of work. Instantly change our picture of reality. Those hidden dimensions would shift from speculation to fact. Our universe would have more rooms than we knew. And physics would start a new golden age, decoding the geometry that writes all the laws. The other path is just as possible, and just as important. What if the evidence never comes, we build bigger colliders and see only familiar particles? Our cosmic surveys find no anomalies in the ancient light. Then the idea of these curled-up dimensions, for all its mathematical beauty, might be a detour. A wrong turn on the map. That wouldn't mean the effort was wasted. Wrong ideas in science aren't failures. They're how we learn the shape of the truth. They eliminate possibilities. They refine our questions. They often lead to breakthroughs somewhere else. The math from string theory has already enriched other fields. Pure mathematics, condensed matter physics. The journey itself expands the tools. It expands the imagination of the whole scientific community. This uncertainty isn't a weakness. It's the essence of exploration at the absolute frontier. We're probing questions that touch existence itself. Is reality built on a stage with hidden, intricate folds? Or is the stage simpler, woven from quantum threads in the dimensions we know? We won't find the answer by staying where it's safe. We have to follow the mathematics into the dark. Build the tools to listen for whispers, and accept that the cosmos may confirm our most beautiful ideas, or it may dismantle them. This pursuit pushes human knowledge to its limits. Patience to its limits, creativity to its limits. It's a search for a unified cosmic story, a narrative that connects the quantum flutter to the galactic whirl. Whether the final chapter includes hidden dimensions or not, the act of searching reshapes our understanding of the universe and our place within it. We are the universe trying to comprehend its own hidden blueprint. We followed this trail of mathematical necessity, from the frantic vibrations of strings to the intricate, curled-up shapes that could stabilize reality itself. This isn't idle speculation, it's a rigorous framework. It proposes hidden dimensions as the architecture that unifies all forces, that dictates the laws we observe. It offers elegant answers: why gravity feels so weak, what the dark shadows of our cosmos might be made of, why our universe seems so finely tuned for existence. Yet for all its explanatory power, the theory remains a map of a territory we cannot directly enter. The Planck-scale fortress guards its secrets well. The experimental whispers we seek are faint. This has sparked a multi-front search: colossal colliders, tabletop quantum sensors, all listening for the faintest tremor of confirmation. It has also ignited a deep philosophical debate about the nature of evidence, about the power of mathematical beauty to guide us toward truth. Whether string theory is confirmed or refuted, its central gift is an expansion of imagination. The idea that our three-dimensional experience could be a slice of a richer, higher-dimensional reality. It challenges our most basic assumptions. It suggests the universe holds layers of complexity and elegance far beyond our everyday perception, waiting to be uncovered not with our eyes but with the curiosity of the human mind. The search continues, not just for hidden dimensions, but for a complete story of our cosmos. And in that search, we are reminded, the greatest discoveries often begin by daring to imagine there is more, much more, to the world than meets the eye.